Okay, let's talk about zero and negative exponents. I know, they look a little weird, maybe even like they're breaking the rules of math. But what if I told you there's a super simple, hidden logic behind them? Well, in the next few minutes, we're going to crack that code, and I promise it's all going to make perfect sense. Let's jump in.
So, here it is. This is the question that trips almost everyone up, right? I mean, multiplying something by itself 2 or 3 times? Easy. We can picture that. But a negative number of times? What does that even look like? It sounds like nonsense. The big secret is realizing it's not about negative multiplication at all. It's a different kind of instruction, one that's hiding in plain sight.
So before we can even touch negative exponents, we've got to unlock the secret of the zero power first. And believe it or not, the key is to start with a piece of math you already know like the back of your hand.
It's the simple fact, right? Any number, as long as it's not 0, divided by itself is just 1. 5 divided by 5 is 1. A million divided by a million is 1. This is our starting point. This is the solid ground we're going to build everything on top of.
Now, let's look at that same problem, but with our exponent glasses on. We know 5 is really just 5 to the first power. And the quotient rule, one of the main rules of exponents, tells us that when we divide powers with the same base, we just subtract the exponents. So 1 minus 1, that gives us 0. Which means 5 divided by 5 isn't just 1, it's also equal to 5 to the power of 0. And that's it. That's the logic. If a number divided by itself equals 1, and it also equals that number to the power of 0, well, then those two things have to be equal to each other. This gives us our first huge rule. Anything to the power of 0 is 1. Period. It's not some weird magic trick. It's just a conclusion that has to be true.
Okay, awesome. With the zero power figured out, we are officially ready to tackle negative exponents. And the key to understanding these guys is a really simple but powerful idea. Think about the fraction bar.
This right here is the most important idea of this whole explainer. A negative exponent has absolutely nothing to do with making a number negative. It's not about value, it's an instruction about place. It's basically shouting at you that a term is on the wrong side of the fraction. You can almost think of it as being unhappy where it is, and it really wants to move.
So how does it get happy? Simple. It just moves. If a term with a negative exponent is upstairs in the numerator, it moves downstairs to the denominator to get happy. And if it's already downstairs in the denominator, well, it just moves upstairs. As soon as it crosses that fraction bar, its exponent becomes positive. It's just a ticket to the other side.
So that's all the theory. But let's be real, seeing it in action is where it all clicks into place. So let's run through a few examples.
Let's start with a nice, simple one. 5 times x to the power of 0. Now, the first thing you have to ask is, what is that 0 power actually attached to? It's only on the x, right, not the 5. And we know from our first rule that anything to the power of 0 is 1. So that x to the 0 just becomes a 1. And we're left with 5 times 1, which is, of course, just 5.
Okay, next up. The first thing we do is just scan the whole thing. We're on the lookout for any unhappy terms with negative exponents. So, is the 3 happy? Yep. Is the y to the 4th happy downstairs? For sure. But look at that x to the negative 2. It's upstairs, and it's not happy. So we do what it wants. We move it downstairs to the denominator, and boom, its exponent becomes a positive 2. And that's it. That's our final answer.
All right, deep breath. This one looks way more complicated, but it's really just a few of our rules stacked together. That negative 2 on the outside, it's the boss. Its first job is to tell the entire fraction inside to flip over. But wait, once we do that, we see that the b term still has a negative exponent. It's still on the wrong side, so we've got to move it down to the denominator. Now that everyone's happy, we can apply that power of 2 to every single piece inside, and we get our final, fully simplified answer.
Now, these rules are pretty straightforward once you get the hang of them, but there are a couple of classic mistakes that are super easy to make. So let's shine a light on them so you can avoid those traps. Okay, this is probably the #1 most important thing to get straight in your head. A negative exponent does not, I repeat, does not make a number negative. A negative exponent is an instruction about position. It tells a term to move across the fraction bar. A negative sign out front, the coefficient, that's about value. It's telling you the number is less than 0. They mean two totally, completely different things. And here's the other big one. I like to call it the trapped coefficient. In something like 5x to the negative 1, it is so tempting to just move the whole 5x thing.
But you have to remember that exponent is only attached to its immediate base. In this case, that's the x. The 5 isn't part of that. It's trapped upstairs. It stays put. Only the x moves.
So you might be sitting there thinking, okay, this is a cool little math trick, but where am I ever going to use this? Well, it turns out this simple idea is absolutely essential for describing, well, pretty much the entire universe, from the tiniest atoms to the biggest galaxies.
Take a look at this number, 1.67. By itself, it's just a number. But when we combine it with a negative exponent, it becomes something kind of profound.
Check this out. This is the approximate mass of one single proton in kilograms. That 10 to the negative 27th? That's a super powerful instruction. It tells us to take the decimal point in 1.67 and just move it 27 places to the left. The result is a number so small, it's almost impossible to even imagine. I mean, just look at that. Can you imagine if scientists had to write that out every single time? It's clunky, it's so easy to miscount the zeros. It's basically a nightmare. Scientific notation, which is powered by these negative exponents, gives us this clean, elegant way to handle numbers that are ridiculously huge or ridiculously tiny.
Okay, so let's boil it all down. What are the big things to remember? Number 1, anything to the power of 0 is just 1. Number 2, a negative exponent is just a signal that a term is on the wrong side of the fraction bar. 3, remember that exponent only applies to its direct base, not any coefficients hanging out in front. And finally, remember this isn't just a classroom exercise, it is literally the language we use to describe everything from atoms to galaxies.
So, I'll leave you with this final thought. We just took something that looked really weird and complicated, and we found a simple logical instruction hidden inside. It really makes you wonder, right? What other parts of math that seem tough are actually just puzzles waiting for us to find the hidden key?